Everything has kind of magically worked so far in C++. Everything kind of magically works in a lot of programming languages, but in C++, usually magic just means that there's some implied stuff that you can customize for your own behavior if you want. So let me give a quick example. So let's say we have, I think we've had something like this before. Okay, right? Makes sense? Now, we can do that, right? So here, we're creating a variable of type A, called A. That invokes the implicit default constructor, which follows that initializer, initializes X, or allocates a new integer on the heap, stores a number 7 in it, and sets X to the pointer to it. Then when A goes out of scope, that pointer will be destroyed. What happens here? Making a copy of A, right? So we're making a copy, but we said previously that all objects need to be constructed, right? All objects are constructed, then you use them and they're destroyed. Whether that's implicit or explicit or whatever, that needs to happen. So how is B actually constructed? So there's actually more than just the implicit default constructor that's created. It also implicitly creates a copy constructor, is what it's called. So the copy constructor is what's used to create an object based on another instance of the same type, and you want to copy all the information. So the implicitly defined copy constructor just copies every field, and so invokes a copy constructor on every field, or for primitive types, literally just copies the value over. Exact same thing for any base classes or superclasses that it may have. If this is if A is a subclass, we, however, can define a new one. And in this case, we might want to, because what will happen at the very end of this block? We'll get a segfault. I can tell you why. A and B both go out of scope at the end, right? So then we'll invoke the destructor on A. So we'll deallocate that piece of memory. Then we'll invoke the destructor on B, and we'll try to deallocate, we already deallocated that pointer, because they have the exact same pointer internally, right? At no point did we allocate a new pointer, because the implicit copy constructor actually ignores any default number initializers you put in. So anything here, it ignores that, because it says, no, I'm copying. So it just copies the value of X into the new thing, and X is a pointer. It doesn't care that it's a pointer, it knows how to copy a pointer. A pointer is a primitive type, it just takes that value and stores it in the same field in the other object, right? So when this goes out of scope, we will be trying to deallocate the same thing twice. Now, what's a useful way to copy this kind of class? We could do what conceptually is called a deep copy, which means we'd also allocate a new pointer and copy the value of whatever that thing points to into the new pointer. So let's see how we actually do that. So we can provide our own copy constructor. The way we do it is we take a const L value reference to A as our only parameter. It's convention to call it other. It's an object that you're copying from. And we'll put in memory initializer, we'll say X is initialized to new int, and we're storing in there value stored at other dot X. We need an empty block. We're not doing anything other than initializing X. Does that make sense? So let's walk through what goes on here. So let's put our sample back in here. So when A is constructed, allocate a new int on the stack or on the heap. We store 7 in that int, and we put the pointer to that int in the field X inside A. We construct B, it calls this constructor, So the syntax, or the signature of a copy constructor is to take a const L value reference to the same type as its only parameter. So we're providing our own version of the copy constructor here. And we're passing A in as a parameter. So then it initializes, or it takes A, looks at the field X in it, takes a value stored at the memory address pointed to by X, and then allocates a new int on the heap, copies that value into the new int, and stores the pointer to the new int in X in B. And so this is an example of a useful copy constructor. Now, one other thing you can do is, we might have said, actually, no, it does not make sense for this to ever be copied. So what we could have done instead then is, I'm not going to do it because I'm going to keep this for the next example. Rather than providing a definition of it, we just could have cut off here and said equals delete. And that says, hey, I know you would have implicitly defined this, but I'm going to explicitly say no, it should not exist. And actually, if it is not possible to copy any of the fields, or if there's any one field or a superclass that cannot be copied, then A cannot be copied as well. So there is no implicitly defined copy constructor if it would not work to have an implicitly defined copy constructor, so if any of the fields cannot be copied. Now there's an efficiency problem that can arise here. And that, so let's say we have A like this, and then what if instead of creating B, we say return A. So what happens here? We create a new object, because A is about to go over scope, so we create a new, what happens here actually is it creates a new object that's owned by the function that called this function, because that's the scope that the return value is going into, right? Whatever called this function that these two lines of code are in. So we create a new instance of A in that context, but using the copy constructor, right? So what happens? Here we create a new int on the heap. Here we create a new int on the heap and copy the value in, and then immediately afterwards we destroy the old one. Would it not have been more efficient to just reuse that pointer because we know we're going to we're about to deallocate it anyway, and rather than allocating the thing, right? So what this is doing here, logically, is we're not really copying A. We're copying and then destroying the old thing. So logically, we're moving A to a new variable that's owned by the calling function. So similar to a copy constructor, there's something called a move constructor. So a move constructor takes a non-const R value reference, and I cannot draw. Ampersand again. R value reference. Quick double check. What type? If I use other in an expression here, what type does it have?
Like the A type?
Yeah, its type is A.
Yeah.
What value category is it? It's an R value reference, but it's a variable, so its value category is L value. So that means, oh, and is it const? No, right? Because there's no const before A here, so it is not const. So it's a non-const L value, which means that it can be modified. So we can start by initializing the member X to other dot X, because remember we said we were going to just reuse that pointer. But then we have to make sure that it doesn't get deleted when the other goes out of scope, because this would only ever be invoked if other is about to go out of scope. So what we can say is we can say other dot X equals null PTR, which is the built-in constant in C++ for a null pointer. So now we can say that. So this would create a new instance of A, right? That's invoking the default constructor A with two curly braces. Is saying it's call the constructor A, don't provide any parameters, so it calls the default constructor. Then we're returning it. So then it'll immediately move it to a variable of the parenting, but it won't do a new allocation and then a free. It will just call the move constructor, because this is not an L value, this is an R value. So it binds to an R value reference rather than a const L value reference. And so we just end up moving over the pointer and setting the old one to null, and so forth. And that's safe to do because delete, unlike free in C, delete on a null pointer does nothing. Does not crash. It's defined, it's valid to call delete on a null pointer specifically to very easily support standards like this, and because if you call delete on a null pointer, you probably just meant for it to do nothing. In principle, yeah, so what the move constructor should do is it should copy, like logically copy all the information over. It should clean up the old object, like we said, by setting it to null, but it should still leave it in a valid state. The reason is, so in this case, we said it doesn't matter since it's about to get destroyed, but it should still be valid to reuse the object. So commonly, how it's put is, it should leave the object in the same state that it would be if it had just been default constructed. Doesn't really apply in this case, because our default constructor here actually does an allocation, but in a lot of cases, the default constructor will just represent like an empty thing. So that could, like for a type, like the built-in vector type, the default constructor for vector is an empty vector. And then you can start pushing elements onto it. But then if you end up invoking the move constructor and move that vector somewhere else, the previous variable is just left in as an empty vector. Still valid. It's a perfectly valid empty vector, but it's empty. Now, why that's important is you can force something to use the move constructor. Or in any other way, force something to use the overload that prefers R values rather than L values, even if your thing is an L value. And that's what the built-in function in the standard library called move, logically. So if we had A, and then we wanted to move, for whatever reason, we wanted to move that into B. We didn't want to copy it, we wanted to move it. We'd say std move A. And how that works is move, the return value of move when passed in A will be the type, the return type of move in that case is R value reference to A, which prefers binding, which like directly matches the move constructor, which takes R value reference to A, and therefore it prefers the move constructor in that case. Yeah, for example, if you had a class that had a field that was a vector of ints, you might have a constructor that takes a const L value reference to a vector of ints. And you may also have a constructor that takes an R value reference to a vector of ints, which is similar to a copy move constructor, except it's sort of you're copying or moving from a different type, so not from the same type. And why you would do that is if you only provided the const L value implementation, which is sort of the normal, like not fancy way of doing it, then in some specific cases you would be copying the whole vector into the field in your class, and then the vector that you just copied from would be destroyed, which means that you just had to allocate enough dynamic memory to store all the contents of that vector, copy all the values over to that new vector, and then the old one was just destroyed. It would have been more efficient to just move the value. And again, you can force it to move, which would then result, again, say if this was of the built-in type std vector of whatever, after you move from it, it just becomes an empty vector. And all the built-in types, like all the standard library types, follow that convention. In order to fully support copying and moving, you also want to define copy and move assignment operators, which are very similar, except that you always want to return a non-const L value reference. So and I'm not going to write out the whole type definition from before, but for that type, the copy constructor would look like, or so the copy assignment operator would look like this, so con new int dereference other x, and you finish off by, so you know that this is the pointer to the current object, so if you reference this, that's a reference to the current object, or technically, that is an L value representing the current object. So that's generally what you return from the assignment operator. And then, similarly, the move assignment operator takes our value reference to A. In this case, we just set x to other.x. Actually, probably in both of these cases beforehand, we'd want to delete our current x, right? Because we may have a current int pointer stored in it. And actually, here we may have wanted to check, is other.x not null? I'm not going to rewrite that now, but it would have been a good idea to say, is other.x not null, in which case, set rx to null. If it's not null, allocate and copy. Depends, of course, on the use case of our type here. And then here, so we could say delete x equals other x, other x equals null ptr, and return the value pointed to by this. Does that make sense? So we're implementing the exact same functionality as copy and assignment construction, except that now we have to deal with the fact that the type is already, or that the object is already constructed, the current object is already constructed and already has a value, and that we have to cleanly get rid of before we copy or move in our new value. But in either case, the copy and move logic is very similar. And these are also implicitly defined automatically and can be explicitly deleted. Same spiel as the assignment, as the copy and move constructors. And as I said before, it's possible to find a copy and or move constructor and or assignment operator that takes a different type. So the constant L value reference and or R value reference to a different type, and then that would allow more efficient construction for some of the fields. As I said before, the example of a class that has a vector field. All this is really idiomatic in C++. It doesn't exist in this nature in any other programming language, but literally everything in C++ runs on copy and move semantics. Everything in the standard library, everything in common third-party libraries that you may end up using. And the idea is that you use it to make libraries and classes and whatnot that just work for whatever just working means for your specific use case. You can customize it to exactly your use case. So you can have an object that does something intelligent when it gets destroyed. The destructor is, again, part of this whole system. You can have an object that, especially for objects that represent physical things like motors on the robot, you might say, well, either the object is just a very light wrapper and contains no state itself other than the port number, or you can say, okay, the object represents the motor itself, so the object maybe cannot be copied. You can't make a copy of a motor, right? But the object can be moved because there's a lot of cases of types that can be copied but not moved because it doesn't make sense to be able to create a second copy of it, and then there may be things that you have to track in order to make sure you don't do a double delete like we were talking before, but moving it is virtually always safe, and so forth.